Welcome. One of the biggest challenges in AI is getting a model that's not just book smart, but, well, street smart. How do you build something that works brilliantly out in the real world, and not just on the data you trained it on? Today, we're going to dive into exactly that, the practical techniques that make it all happen. So here's our game plan for today. First, we're going to get right to the heart of a super common AI problem, overfitting. Then, we'll look at the tools we can use to fight it. From there, it's time to put on our lab coats because we're going to design and run a real experiment. After that, we'll dig into the results, and finally, boil it all down into some key takeaways you can actually use. All right, first up, let's define this thing we call the overfitting problem. It's a great question, isn't it? You could have this AI model that seems like a total genius during training. It aces every test you throw at it. But then, you release it into the wild with new data, and it just falls apart. So what is going on here? The culprit here is a little something called overfitting. The best way to think about it is like a student who crams for a test. They don't learn the concepts, they just memorize the exact answers to the practice questions. So yeah, they might get a perfect score on that practice test, but give them an exam with slightly different questions, and they're completely lost. Our AI is doing the exact same thing. It's memorizing, not learning. So, how do we get our model to actually learn the concepts instead of just memorizing? Let's introduce two really powerful tools for the job, Dropout and Weight Decay. Okay, first up is Dropout. Imagine you're coaching a basketball team, and at every single practice, you randomly tell a couple of players to sit on the bench. Well, the rest of the team can't rely on their star player always being there to make the shot. Everyone else has to get better, more versatile, and stronger as a whole unit. Dropout does basically the same thing to our AI, forcing the entire network to become more robust. Our second tool is Weight Decay. You can think of this one as a penalty for overcomplicating things. It gently nudges the model to find the simplest, most elegant solution to the problem. By discouraging all that extra complexity, it helps the model see the bigger picture, which makes it way more likely to perform well on new data. And what's really cool is how simple this is to actually implement. Right here in the code, when we're defining our neural network, we can just pass in a dropout value. That one little parameter gives us control over this entire powerful technique. It's pretty elegant. Okay, so we've got our problem, overfitting, and we've got our potential solutions, dropout and weight decay. But what's the right dose? What are the best settings? To figure that out, we can't just guess. We need a solid scientific experiment. And this is our battle plan. We're setting up a grid of all the possibilities we want to test. We're going to try 4 different levels of dropout, from 0 all the way up to a pretty aggressive 60%. And for each of those, we'll test 3 different levels of weight decay. You do the math, and that gives us 12 unique combinations to pit against each other. And here's exactly how we'll do it. For every single one of those 12 combos, we build a totally fresh model from scratch. We train it for 20 full cycles, or epochs. And then, and this is the most important part, we see how well it performs on a validation dataset. Data it has never seen before. That's the only way we'll know if it truly learned the lesson or just memorized the test. Okay, the experiments are finished, the models are trained, now for the moment of truth. Let's dig in and analyze the results. So, did all this work pay off? Did our tools actually make a difference? Let's see what we found out. Here it is, our final scorecard. Now we've sorted everything by this avval_r² column. Just think of that as its final grade on the unseen data. Higher is better. Right at the very top, we have our champion, a high dropout rate of 0.6 with a tiny bit of weight decay. But now look all the way down at the bottom. That's the model with no regularization at all. Its score isn't just low, it's negative. That means it performed worse than just randomly guessing. That's a massive difference. Now this graph, it shows the beautiful chaos of a real machine learning experiment. Each one of those lines is one of our 12 models, learning over time. Yeah, it looks a little messy, it's noisy, but that's reality. You can see the patterns starting to emerge. The goal is to find the line that not only gets high up, but stays there consistently, in that top cluster of performers. To make that a little clearer, let's just zoom in on our top 3 models. And wow, a really strong pattern just jumps right out at us. The top 2 performers both use that high dropout rate of 0.6. That's a huge clue. It tells us that for this particular problem, our model was really tempted to just memorize everything. Being aggressive with dropout was the key to forcing it to generalize. So, after all that work, what are the big lessons? Let's distill this whole experiment down into a few key takeaways. Okay, here are the big ones. First, regularization isn't just a nice to have, it is absolutely crucial. The model without it was a total failure.
Second, we found our winning combo for this problem: high dropout, a little weight decay. Third, and this is maybe the most important lesson, you have to experiment. There's no magic one-size-fits-all setting. And finally, notice how the most stable model won, not necessarily the one with the single highest peak score. Consistency is king.
Which kind of leaves us with one last big question. You need this very structured scientific process to test everything methodically. But you also need intuition and experience to even know what to test in the first place. So, is building a great AI model more of an art, or is it a science? I think the real answer is it's the perfect blend of both.